Hello everyone, this video covers sections 4.5, possibly also 4.6, we will see. The title is Adaptive Quadrature. So before we go to that, let's just review what we have done so far. So far, all we did was technically composite quadrature methods, which includes the trapezoid and includes Simpson. And even though these methods mostly work well in most situations, the main disadvantage is that they require equally spaced intervals, or in other words, the value for h has to be the same throughout the process. I mean, h changes, but once you get a value for h, you have to use it all the time. Now, that could be particularly bad for something like this. Let's say you have a graph that looks something like this. So you can see here that you use equally spaced intervals, where the value for h is the same. This approximation is not going to be as good as this one. So therefore, what we want to do is, for this part from here to here, you want to use a smaller h to get a better approximation, and here you can use a bigger h. And in essence, that's what adaptive means, that you're going to change the values of h to adapt to whatever problem you have. Now, adaptive methods are usually very popular because they provide approximations to a given tolerance. So usually to approximations to a given tolerance, and that's technically the main point of this video, you'll see, or at least for section 4.6. I think at the beginning I mentioned this was section 4.5, so we're actually going to start with section 4.6 and possibly to section 4.7, so sorry about the confusion. So again, adaptive quadratures are popular because they usually provide approximation to a given tolerance, which we'll work on that today, and also because they are efficient. And efficient is because they will rely on methods from before, like the trapezoid or Simpson, which are very easy to implement. So therefore, the goal or idea here is going to be the following: is that suppose we want to approximate the integral from a to b of f of x dx to within a given or a specified tolerance, which for lack of a better name we just call it epsilon, which has to be positive. Now everything is going to be based on Simpson's method. So this is the original Simpson's method. We will use the following notation. S of AB is going to stand for the original Simpson's method. And notice this is the original one from section, I believe, 4.3. Now, if you look to the composite Simpson, this is the formula we have for the composite, where this is the error function. So pay special attention to the error function. So this is for the composite one, and this is for the original Simpson's rule. But very important, keep track of the notation. So this is the notation we will be using. So the idea is going to be pretty simple. We're still going to go from A to B, but now we're going to cut this in in 2, and we're going to apply the original Simpsons to this to this interval. So we'll apply it to this part, which will give you this, and then we'll apply the also original Simpsons to the second part, which is this, and that will give you this part. Recall that h is equals to b minus a over 2, so therefore you do a plus b over 2, it should give you a plus h, so you should check this. So that's why this is technically evaluated at this point. Therefore, if we combine these two, then the approximation to the integral from a to b is going to be equals to this, which is this part, plus this part, which notice the connection to this right here. So therefore, you combine the two error formulas, you will end up with this. Notice that 2 to the 4 is 16, so that's why we get a 16. And b minus a is equals to 2h from here also. So therefore, if you multiply by 2h, then this will give you h to the 5th, and these two will cancel one of the 2's, so that's how the 180 becomes the 90. Therefore, if we combine this equation and this one, okay, so you combine these two, we'll get the equation on the next page, which is this. So notice that this one has Cassie, this one has Cassie by itself, and this one Cassie tilde. So this is the last equation we have. This was the original Simpson. So from here, making the assumption that Cassie tilde is equals to Cassie, then from here, this implies the h to the 5th power divided by 90. You take the absolute value, okay, of the fourth derivative of Cassie, then this should equals to 16 over 15 times s of a b minus s of a plus b over 2, and then minus s of a, okay, so it should be the s outside, minus s of a plus b over 2 all the way to b. Now, where does this 15 come from? It comes from the combination of these two, assuming that these are the same, so you should check. This is what you get. Therefore, from here, this implies that the absolute value of the integral from a to b of f of x dx minus s of a plus b over 2 minus s of a plus b over 2, which is the original Simpsons broken into two parts, that this is approximately equals to 1 over 16 times h to the 5th divided by 90 times the fourth derivative evaluated at some Cassie, but this is approximately equals to 1 over 15 s of a b minus s of a plus b over 2 minus s of a plus b over 2 and b, an absolute value. How? Well, remember that this is equals to all of this. And clearly you can see that this 16 will cancel with this one right here. Therefore, this implies the absolute value of S of AB minus S of A plus B over 2, and then minus S of A plus B over 2 and B, this is less than 15 epsilon, or the integral from A to B of f of x dx minus S of A plus B over 2 minus S of A plus B over 2 and then B, that this is less than epsilon. Right, so this is the important part here. This implies that this approximation is 15 times better than this approximation, which is a very good improvement. So this will be 15 times better than this one, just by breaking the interval into two parts. Alright, so let's do an example and see how this compares. So let's say you want to integrate x squared e to the minus x dx from 0 to 1. Okay? So clearly here the value for a is 0 and b is 1. Now the exact solution, which is easier to check, is equals to 2 minus 5 over e, and this is around 0.1606027941. Okay? Right, so therefore if we start with S of 0, 1, which is just the regular Simpsons, you can check that this is 0.16240168. Right, so let's use the new version. So first we need to find S of A plus B over 2. So we're still using the same formula as this one. So therefore this is the same thing as finding S of 0 and 1 half. And you should check this. This is 0.02 AA 6107. Then it will use the same method, but now from 1 half to 1, this is equals to 0.13186140. Right, so therefore you combine the two, S of A plus B over 2 plus S of B plus A over 2 to B. You should definitely check this. This is 0.072247. So now let's compare if it is 15 times better or not. So now the absolute value of the integral of e to the x times x squared dx minus S of 0, 1. And again, just stop the video and check this yourselves. This is 0.0017989. And the absolute error, it will use the second method, which was minus, and then S of 0 to 1 half plus S of 1 half to 1. This one is actually 0.001197. And notice that if you do the ratio of the two errors, 0.0017989 divided by 0.000197 is around 15.03, which is true. It's around 15 times better. Okay. And That's pretty much it for section 4.6.